Any other ideas?
About what?
Million.
About our conversation this morning?
Maybe we bring them up tomorrow.
Yeah, but nothing. Okay,
Nothing urgent.
so here we go.
Didn't get that.
Yeah.
But that was already a suggestion by Steiner for the history lesson.
Yeah,
To put the children in a row like that. May I take that? So first, thank you for inviting me, and warm greetings from the Goetheanum. And before I start with my theme, I would like, because it is important for my view on all this, I would like to make a comment, maybe a little bit at the wrong time, but concerning the conversation this morning. I do not feel well when I hear people say science has no worth at all, everybody looks at it in its own way, and so on, as we heard this morning. Because my way of looking at science is not the judgment or the final result. Science is when I can explain how I came to a certain result. And if another person can understand what I do. So it has 3 steps, of course, but I will not go into that now. But if I can explain how I came to that, and the other person can explain, then we can agree on something. So I just wanted to put a little bit of a kick against the shin of the science skeptics. We can come back to that later. And one of the things we had this morning is that many ask for what is the new of anthroposophical science here. And what we had was always like ordinary science, which connected with my further comment is not in itself bad. So even ordinary science brings a lot of to our attention. And but nevertheless, we have this question: what is new? What is where we want to go? And in a way that came out of Judith's contribution and last night and during our conversation, because the whole question of rhythm is something in a way new. So that one looks even at the human organism as a rhythmical organization is in a way new or a few decades old. And similar with the Earth. And the title on the program says about rhythms and Earth evolution, for my contribution now. And that came up in our phone conversations in spring. And I said, okay, I know that Günther Wachsmuth worked on that, and I will have a look at that. But I won't speak about evolution, because the most thing Wachsmuth did in these books about that is retelling us what Steiner described. And then I prefer to read the original. So what I would like to approach is this question of rhythms. Because yes, different aspects of that are there. And one is, Steiner once said, I think in 1917 or so, I couldn't look that up, science in the future will all be about rhythms. all the science in the future is about rhythms. So you see, that seems to be an important theme. And then there is this famous quote by Rudolf Hauschka, who spoke with Steiner about remedies, and Steiner said to him, study rhythms. Rhythms are the bearer, carrier of life. So the rhythms seem to be interesting in our context. And before I start with that, I would like to add another aspect which was already, let's say, in the background or sometimes even a little bit in the foreground. And when we look at least at the, no, not only German, but in the word climate, the concept of climate, of course, it has at first to do with, yes, what it is like in the desert, at the equator, or in the different zones of the earth, how they were discovered by Alexander from Humboldt. We need to celebrate him this year, 250th birthday. And that is the first approach. But when we speak about climate, at least in our realm of language, we even connect that with, for example, soul or social climate. And when we look around the earth these days, think of Bolivia, think of Colombia, think of Syria, think of Taiwan. We can go on and on and on. And I think we have a social crisis, not only a climate crisis, but a social climate crisis as well. When we think around the earth, and these are only examples, I could go on with that. And one can even think, of course, when one starts that way, ecological climate, social climate, one has to think about spiritual climate. And maybe it is more difficult to identify, but what I sometimes think is that one of the most widespread diseases of our time is depression. And depression has to do that when you experience that you cannot connect with the world. That the world around you becomes dark. It's in a way not there, and you can see it with your senses, but it's not there anymore. And that seems to me like people feeling that there are some questions they have in themselves where they can't find an answer in the world around them. The world becomes dark when I have that question. Like when I ask someone a question, he speaks and answers, and I say, "You didn't understand my question. It was all rubbish what he said concerning to my question." And that's maybe a feeling towards the sense world sometimes. And in that way, sometimes I think this whole climate crisis, social climate crisis, spiritual climate crisis is like a call to mankind. We experience much stronger than maybe 30 years ago. Though 30 years ago, for example, most of the scientific basic insight for the climate change was already there. And other things, we had social crisis as well, student revolts. So I'm always careful to say it was totally different 20 years ago. Yes, careful. But a little bit, I have a feeling that this crisis has really to do something with like taking mankind by its shoulders and shaking it. With hopefully. Okay, back to rhythms. We see that, or we saw that rhythms in the realm of anthroposophy and science is quite important. And if you have read this article by Hans-Ulrich Schmutz, then you have seen that he emphasizes the time scale of this change. One would like to say we experience, but mostly we don't experience it. We know about the climate change, as Judith pointed out, mostly by the increase of computing power, which is not bad, but it is it's something interesting. And so Schmutz points out that it's a question of time scale, and I wanted to just look a little bit in this realm of rhythms connected with the earth. Before I go there, I thought in earlier times, I thought there is a piano in this room. Now I see it's outside. Do you know what happens when you have a tone in music and then a second, and then both are very close? Do you know what happens? Yes? Resonate? No, we wouldn't call it that. Resonance is when you have, for example, I play the violin and press the A on the piano very slowly, so it's not hitting the string, and then the violin, and then the piano makes the same. Yes, but when they are a little bit apart, yes, there's a, we call it Schwebung, I don't know the English word, beat, maybe. And when they are farther away, it gets faster. And when they are far enough, there can even be a new tone one can hear. Then you hear three tones. Something. No, I can't try that. We need not. You need to do that. You need a little bit discordant instrument. And sometimes they do that with pianos. You know, there are 3 strings for each tone, and they discord them a little bit that you have a sort of vibrato. One can do that. I'm not an expert on tuning a piano, but I wanted you to experience that rhythms can interplay with each other and create a new one. This is, in the sense of this morning, an ordinary science, but something, a phenomenon that happens. And with that background, I wanted to look at these rhythms around the earth. And what is quite interesting to me is that people wanted to understand ice ages. Why do we have ice age, cold times, warm times, cold times? Can we find a reason for that? So you can say typical 19th century science, they want to have a cause for that effect. But it turned out to be really difficult. And only in the 20s, there was the first publication of this quite famous mathematician, Milankovitch. And Milankovic was the first who tried to connect the rhythms of the ice ages with planetary rhythms. And at first it was rejected. He published again in 1941, and only later the famous Shackleton brought back up his thoughts, and then it was quite more accepted, though it doesn't explain everything. So that is good for us. It doesn't explain everything. So we can look a little bit so that we know what we are talking about. And I decided to do that on the blackboard and only show a few pictures in the end. When we think of the Earth, like that, maybe. We have day and night. And we connect that with the rotation of this sphere. And that is this daily rhythm. And it is interesting. And therefore, I should have mentioned that in the beginning. I think what Wachsmuth really did was, he was the first leader of the science section, and his scientific work is today nearly out of knowledge. Most of my friends in the science section around the world don't know anything about or from his work. And I can understand that. If you try to read that, you would understand that. But what he really did is he looked for rhythms around the Earth, and he looked at the atmosphere as an organ of an organism. I will speak about that tonight a little bit. He tried to understand the atmosphere as an organ of an organism. And the funny thing is, he looked at this day and night, and he found in the literature he did nearly no experimental work himself. I think one can say he did no experimental work himself. He had people who sent him literature, and he had people who did experiments, and especially Pfeiffer in the beginning, but I think he never did. He had so many other things to do. And okay, but what he discovered in the literature, and you find that earlier than Goethe already, and Goethe referred to that, and I think nobody experienced that you have a daily rhythm of the pressure of the air. And a daily rhythm with two maxima, one in the morning and one at noon, in the night and at noon, and in the morning and in the evening, maximum and minimum. I will show a picture about that. And that is much stronger around the equator than here. Humboldt, of course, observed that too. In the tropes, one can obviously observe that easier. And here it is mostly covered by other pressure changes. And he discovered that, and then he looked for an explanation and couldn't find an explanation. And there is some work done which Wachsmuth, as I found out, actually knew about, but he rejected that explanation. But it is today the common used explanation of that there is, by the warming of the air, there is always an impulse to the atmosphere, and then there is a certain eigenfrequency. I think you call it eigenfrequency. Proper frequency. In German we say eigenfrequency, and I thought that transferred IU as a physicist. Eigenfrequency is okay. So like when you have a string on the violin, the string, for example, for A has the eigenfrequency of 440 undulations per second. But there are more. When you hear carefully, you see that the string is not only doing this. That would be the first eigenfrequency, okay? But even doing this. So like this. That would be 1 octave. And so on. So you have the natural tones, the scale we know. And so from octave and then the quint above the octave and so on. And people calculated these eigenfrequencies for a sphere of gas around the Earth. And then you get eigenfrequencies, and they connected this daily pressure direction as the first eigenfrequency of the atmosphere. That is the common explanation today. Wachsmuth didn't know that, or he knew about this research but rejected it for certain reasons and said, okay, there is something science can't explain, so it's the etheric. And that was a little bit the problem with his scientific work, that in my opinion, humble opinion, but that sometimes he looks for things science couldn't explain and then brings in to explain it with the etheric. And the etheric is in that context like a theory like any other theory as well. There's no observation about that or anything. And of course, when a few years later science can understand, explain it, we have a problem. The etheric is thrown out. So that, I think that is one of the reasons Wachsmuth's books are not read so much today. But it was, I think it was really a real step to look at these rhythms and in the atmosphere and around the Earth. And during that time, this mathematician Milankovitch did the same with the Ice Age rhythms. And what one can find is, and what you all know, being good anthroposophists, is that we have this Platonic year, 26,000 something, going through all these cultural epochs. And when you look at the astronomy of this, that is connected with the precession of this axis. I forgot something to bring with me. I wanted to bring a spinning top. Because when you have a spinning top, it rotates. And if it's a little bit not perpendicular anymore, it starts like this. This is precession. And because of the gravitational force of the sun on the Earth, there is this precession too. And that is around 26,000 years. So that is one rhythm which plays a role. Then there is so that is recession. And there is something else. Called mutation. And that is if this axis not only makes this, but in addition this. That can happen with a spinning top as well. And actually, we all know, especially the doctors, that we have this angle here, this angle, about 23 point something degrees. And actually there is a variation between 22.1 to 24.5. So there's a real, some degrees variation in this mutation. And this rhythm is about 41,000 years. And then I want to say something wrong. Yes. And when you put them together, there is this, how we call that, variation, vibration. And mostly they are called together precession. And then the result of that is, I think, 21,000, yes, 21,000 years. You see, it's not a simple addition, of course. If you have A and with 440 hertz and another A with 442 hertz, the vibration is not 2 hertz or not the sum of both. So that is one of these rhythms. Then we know, second, that this Earth is rotating around the Sun. Okay. And we know since Kepler it's about an ellipse, and in one point of the ellipse, focal point, there's the Sun. So when you look at that, even if it is exaggerated, you see sometimes the Earth is closer to the Sun and sometimes farther away. And so this is called the axial and perihelion. And now, two things. One is this, if we think we look from above on the ellipse, okay? Not perspective, but from above, then this will rotate like this. So that's called perihelion rotation. Another rhythm 112,000 years. And another thing is that this, how I made the drawing, is highly exaggerated. Today, the ellipse around the sun is nearly a circle. But that changes. There is again a sort of breathing process. One could do that again like this: circle, ellipse, circle, ellipse. Everything is in motion, as you said. It's not like the watch. And this is another rhythm of about 405,000 years. And it's the change of eccentricity. You know, if the eccentricity is 0, if it is a circle. Both points together, both focal points in the middle. And if they come apart, it becomes an ellipse, and the eccentricity increases. So it's out of center, so to speak. That is the word. And that is changing. So the distance between Earth and Sun is changing between 137 and 152 millions of kilometers. Normally we say the distance between Earth and Sun is about 150 millions of kilometers. That's, for example, in high school you explain the Olaf Römer detection of velocity of light, you use 150. So the eccentricity is between 147 to 152 million of kilometers. So it changes around 405,000 years. So what you see by then is there are many rhythms, and there are more connected with this planetary system where we like to think about the clockwork, which it is not. And of course, in physics, we know that even the simple gravitational interactions of 3 bodies is not totally predictable. And so we have more in our planetary system. Here we speak maybe about 3, there's Earth, the Sun, and the Moon, but then Jupiter plays a role because it's a big planet, and so on. So there are many rhythms and connecting, and then on the climate of the Earth, of course, there are more influences which are not planetary, so they are tellurial, so to speak, like volcanoes, plate tectonics, and things like that, ocean dynamics. And so we see the whole climate question is in between cosmic rhythms and earthly processes and even rhythms. And Now I would like to look at some pictures. Yes. Wow. And it was good. First, this is this one day, you see, 24 hours, the normal day. And these are data collected over 26 days. And then when you get the middle, then you get these curves. I think the red one is the middle. You have this double rhythm during the day, what Max would discover. The red one is the optimized sine curve, and the black one is the middle.
Atmospheric pressure?
Pressure.
Yeah.
Yes.
What did you say?
Atmospheric pressure.
Atmospheric pressure, yes. Sorry, I didn't say that. Just to let you know what we were speaking about when I told you that about Wachstum. And there we have just a picture how we find that on the internet, of course. What is interesting is, in our time, in summer, the distance to the sun is greatest. And in January, it's small. I looked that up for, yes, on the 5th of January next year, we are closest to the sun. So in a few weeks. But that changes, of course, from year to year. But yes.
Which means summer in the north.
Yeah. Yes, yes. January is international, so you're right, of course. Okay. Now, that is, so to speak, what Milankovitch did. He used the different rhythms. And you see here, K, Y, R. 1,000 years. Here, how many years ago? So here's today. And you see the precession, a faster rhythm, and a slower rhythm. This is obliquity. I think that is what we call mutation. Yes. So this of the axis of the Earth. Change of eccentricity. And now Milankovitch tried to calculate the change of the intensity of the sunlight caused by these rhythms. Because he thought when we have an ice age, the intensity of the sunlight should be lower, of course. And then compare that with stages of glaciation. And then you see that there is indeed a similarity between these two rhythms. Hot when it is high, then we have high intensity of the sunlight, cold when it's low.
So the forcing means intensity.
Yes, I think so. In the text it said about the solar changes in the solar constant. It's interesting when you look over this stuff, you see that the total energy which comes from the sun to the Earth is still higher than the total energy consumption of mankind. It's about 10% more. Surprisingly.
Say that again.
So the total energy which comes to maybe for a year, it's power actually what I can compare. The total energy which comes from the sun to the earth in a year is more than the whole energy consumption by electricity and oil and whatever of mankind. That's surprising.
I would have expected it to be 100 times.
No, about one is about 147 something and the other 170 something. So that was the big result, so to speak, of Milankovitch, that he could connect the climate on Earth with these cosmic rhythms. You see these rhythms and you see this. It's that here as a big step. And now I have to look. Aha, the next picture is more or less the same. Just here we have the climate gases, or however we will call them, detected from drilling. And this is 3,000 meter deep. And then you can find a time scale which is about 400,000 years before our time and our time. And then here we have the temperature and connects, high temperature connects with higher CO2, with higher methane. And that is different. We can, we need not to look at that, but there's this correlation between the gases and the temperature. And maybe here, that is again the correlation with the intensity of the sun, as came out from Milankovitch.
Isn't that ice cores? This is earth drilling.
This is, I think, earth drilling because
Must be ice core.
I'm not sure because
It should be ice core.
ice cores because 3,000 meters under the
You're
ground.
measuring, oh, you're changing.
Oh,
Yes.
no, ice cores aren't 3,000 meters, so maybe it is. I think the longest ice core is about 2 miles.
Yeah, it is.
Well,
Yeah.
it's about 3,000.
Oh, that's right. It is. Right. Nothing.
I put the earlier picture again, and then you look at the figures, you see I switched it around because then it is like this, here and here. So, and now, this is the temperature, and now it's not that long, and you have always to look at the scale. This is birth of Christ, and then year 2000. And here's the medieval warm period, so the temperature, and now you see what is happening here. And of course, if you look at something like that, you have to look here. It's only 0.8 centidegrees, so that's maybe not much.
Can you read what the axis?
yes. There is just different places where they measured the temperature.
The German.
different Northern Hemisphere, University of East Anglia, composite Northern Hemisphere, Hartley Center, and so on. And it is in so far important that this is common. This is, here they are, and here they are together. So that the warming is global, not local. And yes, so we could say, and of course we know today that it is wrong, but we could say 0.8, 1 degree, 1.5 degree, isn't that so important? And today we know, of course, that it is important. And we see that in several diagrams. This is, again, the surface temperature, and 1960, 1980, 2000 goes up. And different ways of finding the mean. And by the climate critics was, for a time, was said, but the temperature is no longer rising. I don't know whether you heard that. It was a few years ago. I have a friend.
After 1998.
Yeah, it was, yes, exactly, 2008, 2011, that time. And I have to admit, I have a friend in the network of the science section who is a robust climate change critic. And the problem is, when he writes me an email, I answer that, and then I can get 4 pages email back. I answer that, and I get 7 pages back, and then you stop answering. So, but this is, one can know today that this interruption of warming was just because one took only part of the measurements, and when one looked at the whole, you see here it goes down, but then it goes up again. There's always a variation, but here it goes up again, and that was El Nino. So in these 2 diagrams, one can see that it depends on how one calculates the mean. And that is, of course, always a question with statistics. I don't know, some of us have made statistics themselves. I did. And I observed myself doing that. And I had a certain mathematical approach to a problem in fluid dynamics. And I expected a certain results out of the mathematics. And I changed the statistics by changing the rod of measurement and whatever you can do. And of course, at a certain point, I got my result. And then I stopped changing. And that was not out of evil or something, but one is happy when one gets this result. And I stopped changing. And later I realized that it was okay, and I got my degree. But it is, even if it's not out of bad will, it is a tendency. You expect something, and if you get that, you stop looking. And so statistics is a dangerous field, so to speak, and nevertheless it's extremely helpful and necessary. And that was the point with these problems of the Earth is no longer warming. And of course, I had to put in this. This is 1 year, the famous Mauna measurement, and this is 1 year. That's, Laura, what the leaves are doing. Yes, then the change is this rhythm in the, it's the year, the rhythm of the year connected with the life processes in the leaves. She worked on leaves and color of leaves. So I just put that in because it is necessary there. And here again we have these ice age cycles over a few 100,000 of years, what we saw already in these Milankovitch diagrams. And then we have this. And one sees that it is obvious that is not comparable with that. What people sometimes say, yes, we have that variations all the time, but that is definitely here different. And maybe the last one is this, where we see normally, that is what you find in the article of Schmutz too, it would get colder. But there is this, why he calls it a climate break, not a change, but a break. It goes up in a very, very short time. You can never compare this change with these long-term rhythms. With the climate change today, we speak about 100-200 years. And then here we speak about 200,000 years. That is a big difference. And therefore it is really, yes, an earnest thing. And I would like just to add something to what Judy pointed out yesterday, because someone asked for agriculture last night. Are the agriculture data included? And in Switzerland, we have the Institute for biological or ecological agriculture, which was founded actually by some anthroposophists and biodynamic farmers. And now it's a huge institute with more than 200 scientists. And there are still anthroposophists on the board. And they do a wonderful work. They mainly do work with, for example, guidelines, handbooks for how to farm biological strawberries or something, and to help farmers, and they do research, and they have a very important research which was published in Science about comparing biodynamic, organic, and conventional agriculture. And in this research, they compared the different impacts of, what can I do now? Different farming activities and their output of climate gases. And it is calculated so that one does it that way, that one compares methane with CO2 and then has equivalence. And then you see this, the hugest is the change of forest. Cutting rainforest and putting it for soybeans. That is the biggest impact. That is interesting. Output of N2O, so nitrogen, out of the soil. That is methane from cattle. That is burning of bio stuff, rice, production of fertilizers and pesticides, and manure, and irrigation machines. Machines are nearly nothing. You can play with a tractor. Just to that one has an impression to compare that. So what we do with the forest is really important. And now comes the clue. It's only a few months old. They compared the CO2 equivalents of conventional biological and biodynamic output.
So, because in English, biological is organic.
Organic, okay, organic, we call it biologisch, yes. Organic, biodynamic. And you see that the conventional output of in CO2 equivalents is nearly the double of biodynamic. I think it is important to know that because the farmers are so often blamed for the whole climate change process. And of course, the meat consumption and all that has to do with that, but that is not necessary. And of course, if we go into that, some people would say, yes, but you would never be able to feed the world by that. That is wrong. We have several studies about that too. And to feed the world is just a very general goal. So yes, how do we want to feed the world? Okay, I just wanted to show that because it came up yesterday. That is published in Science, I think in Science or Nature, and in February. Here is still the report of the Research Institute of the Biological, but I have the article Skinner. Yes, and that is interesting, isn't it? I think I'm just like this. Only went over movies. Able to switch that off.
Oh, can you not switch it? I have a question on slide.
Okay.
Too late.
Well, you may not need it, but the Milankovitch cycles for a warm period and then gradual cooling down into ice age. And then they were all abrupt.
Yes.
Over I don't know, hundreds of years, rise and then slowly down. And it looked like on that one figure that we were in that abrupt rise in the present, but we were adding to it.
Yes.
So it was just higher. All the rises got up to a certain level through the last few cycles of temperature. But now we were just getting above it.
As far as I remember, it is still on the downslope. Our time.
Kind of one of them.
Yes, I just waiting for the so Milankovitch. Better down.
So zero has already risen quite a ways.
I see.
Preparing
Yes,
for another
the downslope.
downslope.
The downslope is that.
We're preventing the downslope.
Yes, that's exactly, and that you find in the Schmutz article in prose, so to speak. Now, what I would like to say in the end. Okay, now I have to be careful.
While you're doing that, so that is kind of the argument against natural variation.
Yes.
That if the natural variation were continuing, it would have continued to cool.
One argument, yes. And of course, the most important argument is the time scales.
Yeah. Okay.
Yeah, the other thing, that the slide that I had last night, in which it talked about the positions of the planets, that was accounting the Milankovitch cycles
Yes.
in that slide. So it was like you saw the
Yes.
the sort of boundaries of that going across, and then you saw what was happening here. So it exceeded the boundaries of the normal cycles. So that's also.
And the abruptness of the cooling, it's always an abruptness.
Or-
It's over
Abrupt
a
war.
long timeline.
It depends on
The warmings of
when you see, you mean, here it's the cooling. And when we speak of 100,000 years, so it's not that abrupt.
Yeah.
Yes, one has to take into account the time.
And it's just the nature of warmth and cooling that causes one to happen faster than the other.
I think that is the combination of these rhythms that is not necessarily a totally sine rhythm again, but it can be like this. And as I said, there are many other influences to take into account. So what we spoke about yesterday, I think that this monocausal thinking is totally inappropriate. So when we just see these Milankovitch rhythms, like here, there is much more involved, like volcanoes and so tellurial rhythms and others. And so it is never that simple that you just get it. Yes.
What I find interesting, and this graph shows it on the bottom, is that the rises in temperature are quick, but the downside.
Yes, that is what you referred
Sorry,
to.
I'm getting that now.
And so that's the sun's activity then. That's the,
I'm not sure why this is quick and then we have this.
but even, I mean, the sun's graph above it, the line above,
Yes.
it also has these, you know, so it's the sun.
I'm not sure. I'm not sure about that. So I would be careful with too early conclusions. But it is obvious that we have this more straight lines. Yes.
So this sun line, is that kind of an averaging of the CO2, CH4, O18, and glacial data to sort of?
No, this is calculated out of Milankovitch approach. Okay, this is calculated so the difference of the solar constant connected with this different rhythm or correlated with this different rhythm. More questions, or can I shut it down?
You brought up an interesting point, and I wanted to make a note on
Yes,
it.
I need a few more minutes. And that is what I would like to say. Two things to wrap that up. One is, when you think about all of this and what we consider today, 1 or 2 centigrade. And when you think about the whole cosmos, until today, we don't know any place in the whole cosmos, for sure, where we have liquid water. That is 100 degrees. Maybe on one of the moons of Saturn, below the ice shield is some liquid water. Out of calculation, one can think about it. And then we have all these questions with exoplanets since a few years. So what we see is, until now, the Earth is the only place where liquid water is normal. Open the tap. And then we speak about 1 or 2 centigrades. Where else do we have or feel the importance of such a small temperature change? In the body. When we have fever, 1 degree is a lot. Not speaking of 2 or 3. And so I sometimes think when we compare that and speak of Earth as an organism, we hear that all the time in the anthroposophical context. When we compare that, is it something like comparable with fever, where we speak in the human organism and a more intense activity of the eye organization? When we have fever, it's the immunity, you know what I mean, immunology, which kicks in, more activity of the eye organization. What does it mean when we look at the Earth as an organism? I would like to just ask the question, because it raises, of course, further questions, because one can think of what is the eye organization of the Earth, what is the eye of the Earth, and that leads in a huge spiritual realm, which is connected maybe with this crisis we experience. And that is one thought I had when working on that. And another thought is that when we think of the sensitivity of this whole process, one can totally, yes, go down on one's knees about the admiration. What is necessary that we have conditions where human beings can incarnate and develop a consciousness like we have, to think about oneself, to observe what am I doing when I'm doing science or art or anything, or doing mathematics. So what is necessary to develop a place like that? Isn't that amazing? That human beings can incarnate. And then when we look at that, what Schmutz points out in his article, that we have all these cosmic influences, and then with this CO2 and these industrial activities, we, in a way, close the connection with the cosmos and have not a cosmic influence which leads to the warming, but a man-made influence. And I read that in Schmidt's article and saw that in the diagrams. And then it came to my mind that how Steiner, in his last letter for the members, some of you might know that, he wrote letters when he was ill and lay down with his illness. He wrote letters hardly every week to the members of the Anthroposophical Society about some anthroposophical themes. And in the last letter, he spoke, it has the heading, from nature to subnature. And when you look at that, and we will come to that, I will come to that on my Sunday lecture, that he very shortly, only very shortly describes what he means with the term subnature. So it's not a book where we can read what it is, but only it's one sentence, and it means a part of the world which is closed from the cosmos, so separated from the cosmos. When you have a car, so technology, it doesn't need the influence of the cosmos. Even the early mills didn't need the influence of the cosmos. Maybe they need the water to turn the wheel, but nearly no influence on the cosmos compared with growing vegetables. And so this relation, or this concept of subnature is something where the process is separated from the broader context or the cosmos. And when you look at this, what Schmidt points out is exactly that the whole earth tends to become subnature in that way, disconnected from the cosmos. And I thought, when we think about what can we do, ask ourselves, what can we do there? Of course, not one answer to that question, but one is, of course, according to this letter of Steiner, when we are entering this realm of subnature, that is okay as long as we go into a supernature in a similar way. And so it's a big question, I think, how can we compensate that by relating to supernature, spiritual world, and so on, in a conscious way? Not that I mean we can just meditate and then we don't need to worry about climate change. Of course not, but it can raise this question. And with that, I wanted to finish, and I will try to come back to that tonight. Okay. Where's the boss? Gone.
Which one?
Yeah.
So I guess time for lunch. Is it okay? Yeah. What time is it? 5 minutes after lunch, so 12:30. Yeah, 12:30. That's good. 12:30. I don't know what the actual schedule is because there are so many rooms involved. This one says 12:30. Yep.
Okay, all right.
So that's this afternoon. No, it's also that separation and technique
Oh,
and morality.
I was told
long
Yeah, well, I know it's like
So, I know it's.
That sounds like, yeah. Oh, Lord,
It's changed. It's changed. It's like it's
Barry, did you send me something today?
Oh. Well, what's going to be, I understood. Anyway, so this sentence, two things. One, we never did it. Finalize it here. So you have it with you. Okay, let's see. So what we realized is Jennifer has sent us some equipment for water work. And maybe it's not here. So that we're hoping will be ready for tomorrow. And we asked Frank to come in. Yes. So you
By
got
your presentation, but then I also had
we have time for conversation.
yeah, I figured I'd do it. And then I also had a question about your first statement.
Well, you don't know how much of that.
Comments about
How
science,
much-
about you feeling well. And you said that we heard earlier, and I wondered if you're referring to what I said.
Of course I did. Oh, yeah.
And Barry took that up. And then we would like to say, I think science is just
So there's two purposes for that.
but that is a
One
nice
is
additional part of it, but it is not
another
everything, because when you can agree things, if you agree on the positive and but everything you said stands, so I'm not criticizing in any way what you said, but I would say that I didn't see any recognition when I did say that would stand. I felt like a wholesale
Then-
chop.
Yes.
So then
this,
we need
how
to
can we imagine
use the method to say something, and I have to repeat it. Is that what you mean? Yeah. And then I can give my answer. We could do that. I suspect.
Well, actually, you know, it's like thinking, well, I would say that, perhaps even the loose way of expressing this.
That is possible in all times. So
I would actually like, you know, to be heard, well, all right.
And also